Whilst BERT is based on the transformer architecture we discussed earlier in the course, it introduces some modifications and has a specific pre-training methodology to make it effective for a wide range of NLP tasks. Let's discuss BERT's architecture in more detail. Think back to our lessons on the transformer architecture. You'll remember we had an encoder block and a decoder block that process the inputs and outputs when training our model. A main difference in BERT's architecture is that it only employs the encoder part of the transformer. This is because it's primarily used for pre-training on large text corpora, rather than from sequence-to-sequence tasks. Other models based on the transformer architecture, like the GPT series of models, are designed with decoders for tasks that involve text generation or sequence-to-sequence tasks. BERT, in contrast, is primarily used for encoding and understanding text, and it's proven highly effective in this role. The BERT architecture consists of a stack of identical encoder layers. The number of layers depends on the specific variant of BERT. BERT Base has 12 encoder layers, and BERT Large has 24 layers. The deeper architecture of BERT Large captures more complex patterns and relationships between our tokens. BERT's input is tokenized text, and each token is represented as an embedding vector. For each of the input tokens, BERT converts this into three types of embeddings. The first is token embeddings. These are the standard word embeddings for each token to convert them into a meaningful numerical representation. The special tokens, CLS and SEP, are also added at the beginning and end of sentences. The second type of embeddings are segment embeddings. BERT can accept pairs of sequences or text segments as an input. Segment embeddings help the model distinguish between different segments. And finally, BERT takes the positional embeddings. These embeddings encode the position of each token in the input sequence. BERT's pre-training objective is focused on understanding and representing language bidirectionally. The model is pre-trained using two primary objectives. The first is masked language modeling. In this objective, a fraction of the tokens in each input sequence are randomly masked, and the model is trained to predict the masked word based on the context provided by the surrounding tokens. The goal of this model training is to try and figure out which words fill in the masked tokens. This forces the model to learn bidirectional context, as it is allowed to see all unmasked words from either side of the masked token. The second is next sentence prediction. BERT is trained to predict whether two sentences in a pair are consecutive in the original text or not. During this training phase, 50% of the input sentences are paired with their next sentence in the original input text. The other 50% are paired with a random sentence from the text. The goal is for BERT to accurately predict whether the two sentences are paired with their next sentence or not. This objective helps the model understand relationships between sentences. These pre-training tasks do not involve generating text, so a decoder is unnecessary for the initial stage of pre-training. The lack of a decoder makes BERT more adaptable for a wide range of downstream NLP tasks such as text classification, question answering, named entity recognition, and more. After pre-training, BERT can be fine-tuned for these specific tasks by adding a task-specific layer on top of the pre-trained encoder. The new output layer we create formats the output to be relevant for the task. So for example, if we wanted to do sentiment analysis, the final output layer would transform our output into sentiment labels. This flexibility and adaptability are key advantages of working with BERT.